take a look at the IMO shortlist, because this is a little bit easy. So let's see what IMO shortlist problems there are. So there, I'll do the more recent ones, so 1959 to 2019. All right, 2020. But I want to do, I don't like inequalities or combinatorial geometry. So let's see, does this have 2020? I mean, this has 2020, right? Oh, but these are, let's see. But there were more than just this. Let's see. Yeah, I wonder why he didn't post it. Yeah, we can go to the official website. I just want to see if they're there. Just hold on 1 second. Why would he not post it here? Okay, but are there any so hold on just a sec. What? Why would they not put up 2020? Where's 2020? That's ridiculous. Oh, okay, 2019 is the last. Okay. So, but yeah, I think I might have done a lot of these. That's the thing. So a lot of these I think I've already solved. So let's
Why don't we start with G8 first?
With G8?
This, or maybe G6.
G6. Okay.
Yeah, because these already came in the exam, and that's a pretty famous one, but we can go for G6.
Oh, G6 I did on my YouTube channel already, I'm pretty sure. Yeah, I did G6 on my channel. G7. Oh, G7, I also did that one on my channel.
It was 2019 G6.
Yeah. This one, yeah, I did that on my channel already. Yeah. Let's do exams. Yeah, let's see. So there was one contest, I think it's, what was it called? Not Serbia, it starts with an S. Oh, Siberia. Let me see. There's this one contest, the All Siberia. Let me see if I can find it. So this contest looked kind of interesting. Yeah, let's try this problem here. Okay. So this is 2009 All Siberian. All right. Oh yeah, there was that one from 3 weeks ago. Let's first try this out. So we have a triangle ABC. Is on side AC. and then we drop perpendiculars to AB and AC. I may have done this problem before. Let's see.
Isn't this just obvious? Because BPT cyclic and SE perpendicular bisector would contain the center of the vector.
Yeah, it's obvious. Okay. All right, let me check for another problem. Maybe this one is too easy. Let's see.
I think we can do the one we left.
Yeah.
2 weeks ago. Yeah,
Okay.
that had a complete later.
Okay, I think that was. I think that was the Festival of Young Mathematicians, right?
Was it? Yeah.
I think it's this one.
Yeah, this one.
Okay, so was it like? I think it was
this one.
Okay.
Yeah.
All right. Uh, 2015 International Festival of Young Mathematicians. All right. All right, so we have a quadrilateral ABCD. It's so it's a circumscribed quadrilateral. Yeah, I'm still not sure the best way to draw these, but let's see. Just draw it like this for now. So okay, so okay, but we want, let's see, we want to rename E, F, G, and H, A, B, C, and D, right? So that's A, B, C, D, okay, the center, they say is I. DA intersects BC at E. Okay, so let me kind of draw it like that. Hey, Enrique. So we got through all 6 of the problems in like the first hour and 15 minutes. So now we're searching through problems on, yeah. So yeah, we're on a roll today. So that is the story so far. So this is a problem actually that we tried. It was like the last problem on like 2 sessions ago. So we're trying to figure it out. So DA intersects BC at E, and AB intersects CD at F. In triangle EAF and ECF, maybe I should switch A and B and C and D. that might, so if A, B, C, D. Yeah.
We replace DD with AC.
So yeah, what if I did this? A, B, C, and D. Let's try this. So we still have BA intersects BC at E and AB intersects CD at F, but okay, so let me hide these tangency points for now, just to make the diagram look nicer. Whoops. All right. Or I could I'm going to rename them later. So in triangle EAF and ECF. Okay, so we draw the in circles of EAF and ECF. Hold on just a sec. Let me, I think I forgot to maximize. Yes, there we go. Minimize this. And we want to show the midpoint of AC lies on the radical axis. So if I call the midpoint M, I want to show M lies on the radical axis of those two circles. Let me rename these tangency points. So I'll call them W, X, Y, and Z. I don't want to delete them because maybe they'll be useful, but whoops. W, X, Y, and Z. All right. Wait, what is oh, this is CD it's showing. Should this be D? Okay. All right. We want to show M lies on the radical axis. So I guess one way we could check that is we could draw the tangents from M to the two circles and show that they're equal. Let me try that for now. So basically, that would mean that MG is equal to MH, and that looks like it is indeed true. Okay, so M is on the radical axis, we just have to prove it. So let's prove it. Kind of interesting. All right. So we want to show the power of M with respect to those two circles is the same. So yeah, the inscribed condition is tricky, but I wonder, so if we let G and H be the points of tangency here, the midpoint of GH lies on the radical axis of them because it has the same power with respect to both. So basically, if we draw the centers of those circles, so center of B and center of E, basically we want to show MJ is perpendicular to KL. I don't know if that's any easier, but it's just an idea. So Yeah, these are not collinear, but we want to show that MJ is perpendicular to KL. That would be one way to do it. Let's see. I'm also thinking of Casey's theorem and linearity of power of a point. So yeah, there's a couple different things I'm thinking of. Okay, so it's kind of like if we consider A and C as point circles, so like a circle with radius 0, the power of M with respect to A and C is the same.
Is JM perpendicular to KL?
What?
JM perpendicular to KL.
Yeah, if we can prove that, if we can prove JM is perpendicular to KL, that would solve the problem. Because J, we know, lies on the radical axis. JG squared is equal to JH squared. And so if JM is perpendicular to KL, that would mean M also lies on the radical axis.
That doesn't really look 90 degrees. Can you measure the angle, please?
Yeah. So yeah. What kind of a dog do you have? Oh,
it is indeed perpendicular.
Yeah. It's funny. So the program, when an angle is exactly 90, yeah, sometimes it does it as a square. But if it's calculating it as like 90.00001, then it will show it as like a curve. It's funny, but yeah, because it's not perfect. So, but it is exactly 90 if you just move the figure around a little bit. So yeah. But what I was thinking is, let's see the chat. J looks like it might be the radical center of all three. KIL looks like a right angle. I don't think KIL is a right angle. Let me check. At least not when I just moved it right now. No. But so if we can show the distance AK, actually, let me think about this. So we have OP. Let's see here. So yeah, showing MJ, I don't want to make it look like those three are concurrent. I kind of like that picture. Maybe, yeah, the Gauss line of ABCD. So, that might help. So Q and M meet at the midpoint of EF. I'm not sure how much that would help. Let's see. So the Gauss line is really interesting. So it says, so if you have, so we have like quadrilateral ABCD. If you take the midpoints of AC, BD, and EF, they lie on a line. And it's not that easy to prove, actually. So, but it's an interesting fact. It doesn't necessarily pass through I. That's just, oh wait, does it? Oh yeah, it does pass through I if they, circumscribed quadrilateral. That's right. So that's Newton's theorem. I forgot about that. So these three, so Q, M, and R are always collinear regardless of the quadrilateral. But if it's a circumscribed quadrilateral, then it will also be collinear with the center of that circle. Yeah, so that's kind of cool. I could just draw that for the heck of it. We want to show M has the same power with respect to those circles. So yeah, Casey's theorem, I know it's not super common, but it's very useful. So Casey's theorem tells us the difference between the power of a point with respect to two circles. Let me check, is MK equal to ML? No. It almost looks like MK is equal to MW, but I think that's a coincidence. Ah, I don't think it, oh, no, it is a coincidence. Okay. Let me draw in a couple more points. Are OS and N? No. Let's just try playing around with stuff. Are M? No way MW and L are collinear. Yeah. So yeah, can we somehow use power of a point or something? I wonder what the radical axis of these two circles is. So that would, yeah, one of my favorite ways to draw radical axes is basically if you look at a common tangent and you take the midpoint, that has to lie on the radical axis, and then it's perpendicular to the line joining the centers. So I don't know if this will give us anything, the radical axis of these two. Yeah, that just looks like some random line. But let me draw, yeah, let me see what the radical center is of the three circles. So that might tell us something. So it's this point right here. That feels kind of just random. Is that like the circumcenter?
Actually, it's not the point.
This isn't the
Point is
radical.
on MJ.
Oh, it should be on IJ, is what you're saying.
It's on MJ.
I'm sorry, it should be on MJ. Yeah. So let's see what I did wrong.
Actually, it is now. You just didn't see the point. It was the wrong point.
Oh, it's right there. So this point is the radical center. Okay. I'm cheating so much with GeoGebra. Okay. So if we let A1 be the radical center, we could try to show that J, A1, and M are collinear. What if I do this? Hold on just a second. So I kind of did something like this. Yeah, the diagram does look really messy. I'm going to delete this radical center of the 3. I'm not sure how helpful that's going to be. What if I might just end up deleting this. I'm just going to check it for now. So if I draw the midpoints of AG and CH, then I wonder if OU and K are collinear. I don't think so. I'm probably going to erase a lot of this. I'm just checking out something. Are OU and K really collinear? I would be very surprised if that were true. Yeah, that's not true. Okay, so basically, MUJV is a parallelogram. Okay, I'm going to delete that. I'm just going to keep that in mind. So MA is equal to MC. Is it equidistant from anything else? Like, yeah, I don't know. I have a couple ideas, but they're all a little bit messy. Let's see. So MK is not equal to ML, right? But so MJ is the radical axis. What if ABC is similar to GIH? That would be interesting. Almost. So yeah, let's try to show MJ is perpendicular to KL. So maybe the gliding principle. So M is the midpoint of AC, J is the midpoint of GH. Is N the midpoint of MJ? No. But
Is ACGS cyclic or no?
A, B, C, D. Oh,
ACG.
ACGH. Sorry. Oops, how did I get point U there? AC.
No, they aren't.
Let me try. Yeah, how do we use that MA is equal to MC? So what if I draw like triangles MKA and MCL? Like I'm trying to think, so this would be a law of cosines bash, which I'm going to try to avoid eventually, but maybe it'll give me some idea. So we want to show that MK squared minus this radius squared is ML squared minus this radius squared. But MK squared, we have MA is equal to MC. Yeah, but we'd have to find AK and CL. Yeah, I want to try to find some special property of point M. It's hard to see though. So we want to use that. This is a circumscribed quadrilateral. Is J the McKell point? That would be bizarre. I don't think so. That would be very bizarre. But I mean, often in these situations, it helps. So this is the McKell point right here of ABCD. Wait, what did I just do? Wait. Oh, because we don't know ABCD is cyclic, so the McKell point won't necessarily lie. So these four circles all concur. I think there's, oops, there's this, 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 and this. They would all pass through that point. That is the McKell point. So I wonder, yeah, this is tricky. Yeah, let's spend another 15 or 20 minutes on this, and then we could try another problem if we're not getting anywhere. Okay. Do you want to put this one aside for now? What are you thinking, Amal? Let's think about it just a couple more minutes. Yeah, definitely. Let me draw the perpendicular bisector of KL. I'm just curious.
By the way, we know here that IAK is 90 degrees.
IJK.
Yeah, that helps in finding some cyclic quadrilateral. Oh, yeah, we can try proving that maybe IMK. No, but IAK is 90 just because IA is internal bisector and K is external bisector.
IAK is 90 degrees. Yeah, we should probably try to use that fact. So yeah, IAK is 90 and ICL is 90. I didn't see that, but yeah, that's
Does this make KALC cyclic?
KALC. Let's see.
No.
Does that? I don't think that actually passes through J. I think that just looks like it, right? Yeah. But yeah. Yeah, I think it's worth using that these are right angles. Like I feel like M is the midpoint. So there's some kind of homosity we could do. Like what if we
is angle KIA equal to LIC? I mean, are those two triangles directly similar or something?
KIA and LIC? Maybe.
Yeah, we know it's 90.
25.7. Yeah, they look similar.
Yeah.
Interesting.
They are both similar. I think we can try using that. And yeah, that gives us a measure to compare CL and AK.
Okay, so let's see how we can show those are similar. They're both right triangles, and maybe we could try to show that AI over AK is CI over CL. That seems like a reasonable thing. But let's just assume they're similar for now, right? What were you thinking after that?
I think we can use this to angle chase something down or try proving that GM is perpendicular. But yet this was just one observation I found.
I mean, yeah, that looks like a really useful fact, though. So I think CIX is similar to CPL. I think that's like trivial to prove. So CIX is similar to CPL, and IWA is similar to KOA. And so I think we can use that to prove that KAI is similar to ICL. Yeah. Yeah, okay, so I can see how to prove KAI is similar to ICL. From it kind of feels like the gliding principle. So
Yeah,
what's,
can you draw the angle bisector of AIC?
okay, one sec.
Yeah, that's not parallel to MJ. I think we could try using the fact that A and C are, I mean, we have similar triangles on A and C, and M and N are midpoints of corresponding joining segments.
Yeah, it looks a lot like the gliding principle, right? So if I reflect I across point C, then I could use the gliding principle and we get MN. I think we're actually pretty close. I have a good feeling about this. So basically, so I prime is a reflection of I over C. And so triangle I prime CL is similar to triangle IAK. And so if we use the gliding principle, CMN is similar to both. And I think that just solves it. Let me think about this. So I don't know if
Yes, CM, and yeah, we also know that ICI prime is. Oh yeah, we can try showing that CMN is similar and then try to prove midpoint.
CN.
Yeah, we haven't actually proved midpoint.
So, but yeah, N is not the midpoint of, yeah, like Enrique said, N is not the midpoint of KL. So, let's think about this. So, M, C, what is the midpoint of KL? Let's see. Whoops, sorry.
By the way, is L, M, N also similar to these two triangles?
MN what?
LMN.
LMN. I don't think so, because then I think KMN would have to also be similar. But let's see. No.
No, it's not.
But let's see. So so if N is the midpoint of KL, whoops. Let me delete this for a sec. So if I take the midpoint of KL, then CMN is similar to both those triangles. So CM is perpendicular to MN, and we want to show that KL is perpendicular to JM. Maybe we could, yeah, I wonder if there's like another way to use the gliding principle. So maybe, it's kind of like, we want to show the angle that AC makes with KL is the angle that MJ makes with MN. Yeah, I am very curious how they would figure this out. So
We can try using gliding on, because J and M are also the midpoint.
yeah,
And
so, but J is the midpoint of GH. So what triangle can I get with G and H in it?
I think SLE and FKG, but they do not look similar though. Yeah, they aren't symmetric.
So basically, we want to show NJ is perpendicular to both GK and LH. That would solve it, right, by the mid-segment theorem. Because, yeah, N we define to be the midpoint of KL, and yeah, J is defined to be the midpoint of GH. So we want to show JN is actually parallel to both GK and LH.
Now, if we define N to be the midpoint, then that's obvious that Jn is parallel to both.
Oh yeah. Does that
Okay,
just,
now we need to prove that Mn is perpendicular.
and we already did by the gliding principle, so I think that solves it.
But yeah, Mn is perpendicular by gliding principle or no?
And we can show that Mn is perpendicular to KL by the gliding principle.
I think this should, or but Jm is the line which is perpendicular to KL.
Oh, I'm sorry. Yeah, Jm is perpendicular to KL. I'm sorry, Mn is perpendicular to AC. I keep messing up. Yeah, no, you're right. So yeah. Yeah, Mn is perpendicular to AC. So yeah, we have like two right angles here. NMA is right and NJF is right.
I think the remaining is just an angle change, because if we focus out on AKGHLC part of the diagram, I think we have plenty of conditions to prove that MJ is perpendicular to KL.
Yeah, like I'm wondering if we let these lines intersect at a point, let's call it X, let's call it I don't know, let's call it R, then RMNA is cyclic. I'm sorry, RMNJ is cyclic. And we want to show MJ is perpendicular. I wonder if KL passes through. No, it doesn't look like it. But the angle that MJ. Okay, I'll go back. So what were you saying?
I was saying that focusing on AKGHLC, the three segments.
AKD and
The three segments AC, KL, and GL.
ACKL and
Yeah, we have three midpoints, and we
Yeah.
also have that K is perpendicular to GL. I think all we need here is an angle change.
So yeah, angle NMA is 90 and angle NJG is 90, right? We just have to show we just have to show KN is perpendicular to JM, right?
Let me try finishing the details. Give me a
Okay. All right. Yeah, I know, I think we're close. So yeah, we would, in that case, we would have like three perpendiculars, NM, NJ, and so all three sides of this triangle.
RFKLE cyclic.
I'm sorry, can you say that one more time?
FKLE.
FJ and,
K.
oh, I'm sorry, can you type it out in the chat for a sec? I'm sorry, I couldn't hear it that well. FKLE. All right, thanks.
Not the N cyclic, I had tried this before.
It almost looks like it passes through Y, but I don't think so. No.
I think we should delete WXYZ here. And here we haven't used the fact that it's circumscribed yet either.
Yeah,
I mean,
we
we can take I to be the intersection of angle bisectors of A and C. We haven't used B and D yet.
We haven't used B and D. Yeah. So maybe we want to use that I, M, and R are collinear. I'm not sure. So I think, oh wait, never mind. Or we could try to show that mk squared minus jk squared is ml squared minus jl squared. Yeah, that might work. Let me try that. Let me see. I think I have an idea here. So we want to show mk squared minus kg squared is ml squared minus lh squared. Um, Yeah, we have three midpoints. J is the midpoint of GH, N is the midpoint of KL, M is the midpoint of AC. Yeah, it looks like we have a lot of information. Is GAI? So I don't think this is true, but let me check it out. I want to see if GAF is similar to HEC. No. All right, let's try this for like 5 more minutes and then I'll move on. Feels like we're close, but I'm not exactly sure how to finish it. So we know NA is equal to NC and NG is equal to NH. Is N the circumcenter? I'm sure we've done this. I don't think AGHC is cyclic. But we know NAC and NGH. I wonder if they're similar. I don't think so, but it's worth a shot. They are similar. NAC and NGH are similar. Huh.
And that's the angle we got for KIA. Yeah, NGJ should be similar to KIA.
Say that one more time.
NGJ.
NGJ.
Yeah, and should be similar to the triangle we found earlier, KIA.
NGJ is similar to KIA.
Because the angle NSJ turned out to be the one we got earlier.
Okay.
We already know that NJ is perpendicular to GJ.
Yeah, so we know this is a right angle. And also, yeah, we have so many similar triangles. Now it feels like the problem has to. So we have NJG is similar to NMA is similar to IAK. I think this kind of might be the gliding principle, because if we basically, let me reflect N over point J. And then if we know A, N, C is similar to G, N prime H, then we could use the gliding principle, but we need like the midpoint of AG and the midpoint of HC. So let me see. Yeah, that would be kind of weird. We're very close because ANC is similar to GNH. So I don't think that's actually the angle line vector. So what if we drew these circles? Now I'm confused. What if I draw? Yeah, it doesn't do anything. All right, you guys want to move on to the next problem?
Yes, please.
All right. Let's see. Okay, so that was from this competition. This one looks. This one's kind of interesting. But yeah, this one might just be like Cheva's theorem or something. Let's see. You guys have a contest you want to look at? Yeah, I don't know which of these I already did. That's the thing. I could try this contest. Oh, this is a short one. Doesn't have any problem.
T3 looks good.
This one?
Yeah.
All right. So let's see. This is the 2016 Golf Math Olympiad. right. So this is a two-parter. All right, so we have a triangle ABC, acute. X is on BC. Let me make C at the top. So A, B, C. So X is like any point on BC, and Y is any point on AC. We draw the circle with diameter AX and the circle with diameter ABY. This kind of looks familiar. And we see, okay, so the first one we see where it cuts AC. And the second one we see where it cuts BC. Okay, so I mean, those are the perpendiculars from X and Y. I don't know if we need to draw those circles. I'm going to hide them for now. So we draw the perpendicular. So this, they call it E prime. And then they call it B prime. It's kind of interesting. And let M be the midpoint of XY. And we want to show that A prime M is equal to, what is A prime? Maybe they meant E prime M, because that would make sense. I mean, we know this, that's kind of trivial. So I'm guessing here they mean E prime. So that's trivial because E prime X is YBX is 90. So that's cyclic with center M. But let's see the second part. Let M, suppose that K1, okay, so we do have to draw those two circles. So suppose they meet at P and Q. So we want to show the orthocenter of ABC lies on the radical axis of those two circles. That's interesting. So basically,
this one is obvious because if we take any two serions of any triangle, then the circles drawn with diameters as serions would always have orthocenter as the radical center. Here the key point here is that the circle drawn with serion as diameter would pass through the foot of altitude.
Would pass through the foot of the perpendicular. So I'm going to draw the orthocenter one sec. Wait, that's not the orthos. I thought it was 4. Oh, it's AB1. Whoops, is the way I labeled the point. Oh, this should be like B prime. Whoops. But basically, I think Amal, you're saying it's obvious. So we have to show the power of the orthocenter with respect to those two circles is the same.
Here it's a well-known property that power of orthocenter with any serion as diameter is SA times SD.
Okay.
We can just draw the two altitudes from A and B.
Okay, so if we draw the altitudes from A and B, yeah, basically the circle passes through them. Yeah, they pass through those points. And so the, okay, so yeah, Yeah, it's just power of a point because FA times FB is equal to FB times FB. Yeah, so that's kind of trivial. It has the same power perspective. Okay, so this problem was too easy. Let's see if we can find a harder one. What's a good contest? Let's see. You want to try an old USAMO problem? USA? So yeah, the new ones are going to be really hard, but let's see. This one might be easy, but I'll try it. Oh, that's weird. Okay, so this is USAMO 2020. Anmol, so you do want to do this one or you don't because it's an Evan Chung's book? Oh, we should do. Okay. All right. So ABC is an acute scaling triangle, and let me break up. Okay, there we go. All right. So we have an acute scaling triangle ABC. M, N, and P are the midpoints. M, N, P. Obviously, they lie in the 9-point circle. And let the perpendicular bisectors of AB and AC intersect AM at B and E. I feel like I might have done this problem a long time ago. D and E, and BD intersects CE at F. We want to show that ANFP is cyclic. Okay, this looks like it might be a legit problem. We want to show ANFP is cyclic. Wait a second. Oh, whoops. Yes. So we know NP is parallel to BC. Whoops. So we could try to do a homothety. If ANFP is cyclic, that basically means that I feel like I've done a problem like this on my channel before. So that means that like F, that means if we let AF meet the circle at a point G, then F is the midpoint of AG. So yeah, if we could show F is the midpoint of AG, that would solve it. So let O be the center of C. Yeah, so basically we want to show OF is perpendicular to AG. Didn't we just do a problem like this on my channel very recently where I show F as like the midpoint of AG? I feel like I did. But I mean, so what we could do is we could let F be the midpoint of AG, and then we could show that C, E, and F are collinear, and then by the same argument, B, F, and D would have to be collinear. So I kind of like that. Okay, so let F be the midpoint of AG, or we could call it F prime. And
GFOC or cyclic.
GFOC,
BFOC.
DFOC, or DFOM, I guess.
No, BFOC.
Ah, BFOC. All right, so
It's just angle chasing.
it's just angle chasing. Because yeah, and I think this looks really familiar because because like angle OFG is 90 degrees.
If
So
it's dumpty or anti-point, I'm not sure.
so yeah, it might be the dumpy point. But is AF a symmedian? I think AF is a symmedian. Yeah. So wait, but actually, I don't know if I can actually solve this way because G. No, because yeah, I don't think I can just let F be the midpoint of AG because I define G by taking the intersection like this. But yeah, basically, I would let G be the symmedian point. I would let AG be the symmedian, and I would let F be the midpoint of it. And then I could show C, E, and F are collinear. And then B, F, and D would be collinear by the same argument. So I think that would do it. Let me check that it's actually a symmedian. But yeah, it should be. So 26, yeah, looks like a symmedian. Okay, so I draw the symmedian and I let F be the midpoint, and then I want to show that C, E, and F are collinear. And is that easy to show? So I could probably hide a bunch of things. Oops. So, okay, so you said BFOC is cyclic. And that's true because if we let the symmedian meet this circle at another point, I mean, basically, yeah, if the symmedian meets the circle at a point, then HB and HC are tangents to the circumcircle of ABC. And then, wait, is that actually true? I think it has to be, yeah. If BF and yeah, there's so many different things that I'm seeing, but But the thing is, we didn't know that BFOC was cyclic. We're trying to prove it, but since angle O, like, yeah, I guess first we draw the tangents to the circle, and then by properties of the symmedians, those are collinear. Yeah. So yeah, and then angle OFH is OBH is OCH. So yeah, so that's cyclic. And then we want to show that C, E, and F are collinear. And that's probably also obvious. So how do I show that C, E, and F are collinear? So EAC is GAB is BCG is ECA. So E and F are like isogonal conjugates, right?
How did we prove is on BC and the other point? I couldn't see.
So you've proven that.
What is the point at the bottom? I cannot see H. How did we prove F is on BCH?
How did we prove that F is on the circumcircle through BO, C, and H?
Yes.
Basically, we proved it because we let F be the midpoint. And so, yeah, so angle OBH is 90 degrees and angle OFH is also 90 degrees because angle OFB
right.
is 90.
Yeah, I see.
So, yeah. But now, yeah, we have to show C, E, and F are collinear. I'm not sure if that's just obvious. So angle FCB. Yeah, you can write up the angle. Oh yeah, angle ECA is equal to angle EAC is equal to angle BAG. Yeah, I feel like it's obvious. Hold on, give me a second. So we just want to show ECA is FCA, but ECA is EAC, which is BAG, which is BCG, BCG, BGC equals ACF. Because since CB is also symmedian in AGC. Yeah, so yeah, so that proves it. So yeah, I'm just gonna write it out. All right. So we're speed running USAMO. Isn't this great? It's the older USAMO, so it's not as hard as the newer USAMO, but we're still speed running it. Okay. So so let the tangents to ABC meet at H, or at B and C. Let O be the center of the circle ABC. Then, and let AH meet the circle at G. So that means that AG is a submedian. AG is the A submedian. All right. And then let F be the midpoint. I really should call it F prime, I guess. Of AG. And then that means that angle OF prime G is 90. And so that means that OF prime BHC is cyclic. So we can draw that in. And then we have angle. So ABGC is harmonic. So it's a harmonic quadrilateral. So that means that we also have angle AC. Angle BCG is equal to angle ACE. I'm sorry, BCG is ACF prime. Yeah. And so therefore we can do an angle chase, and we have angle ECA is equal to angle EAC is equal to angle BAG is equal to angle BCG is equal to angle F prime CA. So that means CE and F prime are collinear. And then similar, by the same argument, so yeah, I hit a bunch of stuff, but by the same argument, B, F prime, and B are collinear. So that means that F prime equals F. And then from there, it's obvious because AFO equals APO equals, so we have angle AFO equals angle APO equals angle ANO equals 90. So that means that ANFP is cyclic. All right, let's try another USAMO problem. Let's see. What's another good one? You guys like this one? It's a little bit long, but it's kind of interesting. This one I think is actually really easy, even though it's a number 6. I think I did this one before. Let me see if I can find a shorter one. too complicated. This one's kind of interesting, although it might be a little easy. I think I might have done it too. Let's try it. We only have 10 minutes left. All right. So this is USAMO 2010. So we have a pentagon inscribed in a semicircle with diameter AB. Let's draw that semicircle. So here's AB. O is the midpoint. Then let's draw our semicircle. Why not just draw the full circle? Peak. So X, Y, and Z are just random points. Let me maximize. And oops, what did I just do there? P, Q, R, and S. So Y onto AX, BX, AZ, and BZ. Interesting. Okay, so we need to draw the lines actually. So it's kind of like we pretty much have an orthocenter. It's probably worth drawing this point. So AX and BX and AZ and BZ. So we have like a bunch of many perpendiculars. AX, BX. Okay. So PQRS. E. Yeah, this is a kind of complicated problem statement, but it doesn't look that complicated of a diagram, so I kind of like it. PQRS. Prove that the angle between PQ and RS is half of angle XOZ. Interesting. Seems yeah, it does seem solvable by angle chasing. So yeah, like angle XBZ is half of XOZ. So I just need to check that those are equal. So the angle between PQ and RS, that lie on AB, yes. So we'll prove that, but it's kind of like just saying that QDBS is cyclic, right? Yeah, because YQBS is cyclic and YPRA is cyclic, and they both pass through the altitude from Y. So I think that just solves it, because these circles, before we even basically, those are cyclic and they concur because they pass through the altitude from Y to AB. And so basically we just need to show that P, Q, and D are collinear, and S, R, and D are collinear, and then it's kind of just like angle chasing, right? So Yeah, how do we show? I mean, even that just seems like an angle chase.
Using Simpson line, we can prove PQD are collinear.
Okay, yeah, because those are the three altitudes. Yeah, so the Simpson line says that P, Q, and D are collinear. And similarly, the Simpson line says R, S, and D are collinear. And then it has to be an angle chase, because angle PDS, it's PDY plus YDS. Let's see, is it, which is P, I'm trying to see if it's that easy. Which is, it would be XAY plus YBZ, which is half of angle XOZ. So yeah, that's it. All right, so we can move on to the next USAMO problem. Or do you guys want me to write it up or just move on to the next one?
How did we prove the angle inequality?
Oh, so angle PDS is angle PDY plus angle SDY, and angle PDY is angle PAY, which is angle XAY. So when you add up those two, it's angle XAY plus angle ZBY. So XAY is half of arc XY, yeah. ZBY is half of arc ZY, and so they add up to half angle XOZ. That seems easy for a USAMO 2010. 2010 isn't that long ago. Let's see. Let's try this one. All right. No, I didn't make it to USAMO. I wasn't good enough. But yeah. So this is what year is this? USAMO 2014. Let's see. Well, there's such a big space here. Let's try it now. There we go. There we go. So ABC is a triangle with orthocenter H. We're going to wrap up in 5 minutes, but maybe we could solve this super quick. So, P is the second intersection. Okay, so the circumcircle of AHC, we know it's like the reflection of the circumcircle of ABC. Oh, AHC. It's a bisector. Okay, so draw the angle bisector. So we know those two circles are congruent. The two circles are reflections across AC. So we call this P. Wait, let P be the second intersection of. Well, what is the second intersection, right? Because. Oh, BAC. I'm sorry. So yeah. So P is this point. And X is the circumcenter of APB. Whoops. Prove that, and Y is the orthocenter of APC. It's all the way out there. Wow, is that right? Oh no, I said it's It's not doing it right. What? Y equals triangle center. Let's do this again. Y equals triangle center A comma P comma C comma 3. There we go. That almost looks like the circumcenter of APC. Oh, I think it's 4. Yeah, it has to be 4 instead of 3. There we go. So the orthocenter of APC actually lies on the circumcircle of ABC. So we have to show the length of XY is equal to the radius of ABC. Okay. So is it obvious that the orthocenter of APC lies on the circumcircle? So the reflection of it, I think it might be obvious because, yeah, because whatever the orthocenter of APC is, when we reflect it over AC, it should lie on the circumcircle of APC. So yeah, it's just symmetry. Okay. So we know Y lies on the circumcircle of ABC. X, is XY perpendicular to BC? It looks like it. I wonder if that's just like a symmetry argument, because X lies on the perpendicular bisector of AP. And I think this point is like the reflection of Y over AC. Is that actually true? I don't know if I'm making. You should check just to make sure I'm not making that up. It's not. But somehow XY is perpendicular to BC, and let's draw. Let O be the center of C. Is AP, so AP is an angle yeah, so basically this, we want to show XOEY as a parallelogram. Oops. So XO is perpendicular to AB, and YE, I'm betting there's also a way we could show it's perpendicular to AB. Okay, I don't think we have time to solve this problem fully, but if I had to guess, first we show XO is parallel to YE by showing that they're both perpendicular to AB. So that's probably an angle chase. And then we show XY is parallel to OE by showing they're both perpendicular to BC. And then once we know that that's a parallelogram, then we know XY is equal to OE. So I think that's the strategy, and we won't have time to finish it here. But yeah, this was an incredible session. So I'll try to find harder problems next time so that we don't just crush it, unless you guys like sort of searching for problems. But thanks a lot for participating. So yeah, this was a lot of fun. And yeah, I know like some of you are still doing Olympiads, some of you have already finished them, like Ann Mull and Enrique, but yeah, regardless, it's just a lot of fun. So for everyone watching, if you want to join these sessions, email me at mgreenby801@gmail.com. So these are on Sundays at 10 a.m. US Central Time. So check when that is in your country. And I look forward to